Okay, so let's continue by looking at the vibrational contribution to the thermodynamic properties by calculating the molecular partition function for vibration. And remember, for a molecule which has X atoms, there'll be a certain number of normal mode vibrations. And for a linear molecule, that will be 3x minus 5. For nonlinear, it will be 3x minus 6. And each one of those normal modes will have its own characteristic vibrational frequency, and the energy, the quantized energies, will be given for each of those normal modes by this expression here, where these are the Planck's constant, speed of light, and this is the characteristic frequency given in dimensionality of wave numbers, and then n are the nj are the quantum numbers for the different vibrational states of the jth vibrational mode. So given this expression here, we can now calculate the partition function in our summation. One thing that's going to be important, of course, is the characteristic temperature for the vibrational motion, which we can calculate just from this characteristic frequency here, the vibrational frequency. And if we're going to be in the classical limit, we need to be much greater than this. But as you see, when you look at these tables, that for these simple asymmetric, small asymmetric molecules, that these characteristic frequencies, these vibrational frequencies, these characteristical temperatures are all significantly higher than room temperature. So at room temperature, we don't expect much contribution at all from the vibrational part of the partition function. Similarly, with the diatomic molecule, you can see even with hydrogen, it's really spectacularly high, 6,000. Chlorine and iodine. Here, maybe with iodine, which is a really heavy molecule, you can see that we might start having significant contributions at room temperature here. But for the most part, you can see that there's not a lot of contribution, which is what we learned earlier in the course. Now, we can take that energy expression here, and we can plug it into the expression for the molecular partition function, the summation, and I'm going to factor out here the 0 point energy term here, and now I just have the summation here over the sort of the part that depends upon n, and this n goes from 0 to infinity for each of the different normal modes that are present. So we have a product, j equals 1 to mv for all the normal modes. So each normal mode is its own product in forming the overall vibrational molecular partition function. So this summation here is one of the few cases where the infinite sum actually converges to a simple analytical function. In this case, it converges to just 1 over this function right here, where I've made the substitution for the characteristic temperature here. So this whole term up here simplifies to this, and now this product written out has this nice simple form here. And all we have to do is look up these characteristic temperatures for each of the vibrational modes, normal modes, and we can calculate the partition function. Now, in symmetric polyatomic molecules, it turns out that some of the vibrational modes are going to be degenerate. They're going to have degenerate frequencies. So when we do this product here, or the summation after we take the log, we don't need to actually include some of these multiple times that they're going to have the same frequency. So we can actually go to the tables and we can just add if you look in the tables, we can add a degeneracy here. And in this case, they're all 1, but some of the other, some more symmetric molecules, you'll see the degeneracies increase from 1. And so we'll have in our tables a degeneracy and the characteristic temperature. So when you go look these up and you're calculating the partition functions, you just need to get the degeneracy and the characteristic temperature and then do the sum over all of them to get the, and then take the log here to get the log of the molecular partition function. So this is fairly straightforward. Again, you're just going to go to the tables and look up the degeneracies and the characteristic temperatures. You'll plug them in this formula, do the sum. It's a finite number of these. So in case of water, there's only 3. And in case of hydrogen peroxide, there's 6 vibrational modes. And you'll sum over all those modes, and you'll get the partition function. So next then, we calculate the energies and the heat capacity, the free energy, entropy, all using pretty straightforward applications like we've done in the past, and we get these expressions here. So these are all expressions, you just do the sum over all of the vibrational modes that are present here. So this K equals 1 to the number of modes that you find in the tables. So if you look at, for one particular, just one normal mode, what the energy looks like as a function of temperature, you can see that at zero temperature, at 0 Kelvin, we start out with an energy, which is the energy associated with the 0 point oscillation. So there's, the harmonic oscillator doesn't have a zero energy, it has a 0 point energy, and we see that in the molar energy here. And then as we increase the temperature, you can see then it starts to level off and move and follows the classical prediction here. Same thing with the heat capacity. The heat capacity starts out at 0, but then as you increase the temperature, it moves up and eventually goes to the classical limit here. So let's look at a simple calculation. We have 1 millimole of water vapor, again at 400 Kelvin. We want to calculate the vibrational contribution to entropy and the heat capacity, and then see how that compares to the classical limit. So remember, for water molecule, we have 3 atoms, so 3 times 3 minus 6 is 3 normal modes of vibration. That's what we expect to find. Their characteristic frequencies, when we go to the table, are here, and then we can calculate then the molecular partition function by taking these values into the summation, which I'm just going to plug those values in at 400 Kelvin, and have these 3 terms, which you then multiply out to get this 3 terms, and then you finally get that 0.05954 for the partition function. If we then go to the entropy expression, we have this expression here where we can then calculate with these degeneracies and the characteristic temperatures again. So I'm plugging those in to these expressions. I have this term, I've written out 1, 2, 3 for the 3 normal modes, and then this term 1, 2, 3 for the 3 normal modes, and then evaluating these 3 terms are this term, and then these 3 terms are this term, and we eventually get 0.0218, which is our entropy divided by nR. So then we multiply it all through, and we get a contribution of 0.1814 millijoules per Kelvin for the vibrational contribution to water at 400 Kelvin. So it's pretty small. If you go back to the previous values, you can see it's much smaller than what we got with rotation, and certainly much smaller than what we got for translation. All right. To get the heat capacity, we just go back to its formula. I think I left it out here, but let's go back here. We have this formula here for the heat capacity. So we'll go back and plug those numbers into its expression, and that gives us these 3 terms, which we then evaluate out here to get 0.1074, and that's the heat capacity divided by nR. We're putting in the number of moles and the gas constant, and we get 0.8930 millijoules per Kelvin. And remember, the prediction for the classical limit was this should be on the order of 3R times the number of moles, which is 1 millimole. So that's only about 3.6% of what you would have gotten if you had had all of those vibrational modes active and contributing to the heat capacity. Okay. All right, well, that's it for this video. In the next video, we'll take a look at the electronic contribution.